Welcome to my YouTube channel Kadam Academy. Dear friends, still you have studied the various videos. Through these videos you will learn this single degree of freedom, undamped vibration, various videos on the numericals also there. Today we are going to study the pre-undamped vibration, subtypes of the pre-undamped vibration. Under this, the transverse vibration we are going to study, and after that, in next video, you will get the torsional vibration. See, these are the few applications. You can see these are the few applications where the transverse vibration is occur. Due to this, there may be failure. So we have to find out the transverse vibration, how it is there, and when it will going to fail. And these are some softwares they are used. Here the last one, the right one is the software. By using software, we can also find out where it is going to fail, and what are the stresses, and also we can find out the natural frequency of in that objects, all the objects. So these are some glimpses to show you. Okay. Then learning outcome of this classification of pre-vibration. After completion of this lecture, you are going to learn learn the pre-vibration and its subtypes. Okay, differentiate various types of the pre-vibration, and you are going to find the natural frequency of pre-transverse vibration. And also you will learn the relationship between static deflection and natural frequency. What is the difference in a static deflection? Why it is required to calculate the static deflection? And the various types of beam load conditions given to you for your learning purpose. Okay, these are the applications where it is used. And start with the pre-vibration and its subtypes. In pre-vibration, the object is not under the influence of any kind of the outside force. Here the force is applied once and it going to vibrate. It's natural. So there is no resisting force. That's why it's a pre-vibration. Under this, we'll study the longitudinal vibration, transverse vibration, and the torsional vibration. First is the longitudinal vibration. Here, when the particles of the body, shaft or disc moves parallel to the axis of the body, the vibration is known as longitudinal vibration. See, this is the shaft, okay, and this is the disc, and this disc is when force is applied, it will move from this position to this is the mean position. B is the mean position, and it will move like this, and there will be possibility of the displacement from A to B, B to C, C to B, B to A. Like this it will move. And what the statement say, the particle or the shaft or disc moves parallel. See, this is the parallel, moves the parallel to the axis of the body. Means what? This is the longitudinal vibration. This is the longitudinal. Similarly, for transverse vibration, see, this is the mean position B. Okay. This is the movement of this angular movement for this type of the vibration, and which will be the perpendicular to this axis. Okay, if we see this is the axis, it will move like this. Means perpendicular, like this. So friend, here this we can call transverse vibration. In transverse direction it will move, so it is called transverse vibration. And the particles of the shaft disc are move approximately perpendicular. It's not perpendicular, but it's approximately perpendicular to the axis of the shaft. Okay. This is the mean position. This is the extreme position here on this side A, on this side C. So then the vibration is known as transverse vibration. Lastly is the torsional vibration. When the particles of the body move in a circle about axis. See, in this diagram you can imagine. So in circular motion about this axis, this disc is moving in circle about the axis of this body. Vibration known as torsional vibration. The particle of the disc move in circle axis of the shaft, then this suppose this is the B is the mean position we consider, and when we give the this disturbance to this axis of the disc, so what will happen around this axis? So what will happen? It will move from this position A again into position C. Like this it will move, so making an angle theta. Here making an angle theta. So this is the torsional vibration, and this is the subtypes of the free vibration, undamped, single degree of freedom. Okay. So now we are to concentrate this lecture on the transverse vibration. Under this, we know that when the shaft axis disc move approximately the perpendicular. Okay, this is the approximately perpendicular. This is the one more shaft is shown to you, and this is the weight at the end of this one. Mean position it is there. When we move, when we apply this force here once and remove it, will vibrate like this. So it is perpendicular to this mean position. This is a transverse vibration. So one more diagram before we studied vertically, this is horizontally. In such cases, shaft is straight but bent alternately, hence bending stresses are induced. Here what will happen? Here the bending stresses in top of this portion and the tension stresses on the bottom of this shaft. Similarly, what will happen when shaft go downside? The stresses will be there, bending stresses will be there in this shaft. So friend, the natural frequency of this free transverse vibration. So this is the diagram shown to you. This is the shaft with this is weight W. Okay, consider the shaft with the negligible weight, but at the end, free end, the weight is attached at W. Okay, whose fixed end is there, and other end is carries this weight W. And what will happen? Suppose this is the when weight is attached to this shaft, it will deflect. That deflection is nothing but the delta in the static deflection. Due to this self weight, it will get deflected to this mean position. Now the position will be start from here. We are considering from this position the mean position. So from mean position, when we give the disturbance of this displacement of x distance, so it will displace to this position. This is this new position, and this is the mass. Okay, now this weight it is shown with their FBD diagram here itself. Position after the position of this mass after the time t. Okay. So these are the some forces on this one. We will see here in this case, K is the stiffness of the shaft, Newton per meter, and W is the mass of the body in Newton. That is mg. Here is the m into g. The weight of this is nothing but the mg. And when this here m is nothing but the mass of the body in kg. Okay. And del is the static deflection due to the weight of the body in here. This shown in this weight is shown in this W. Okay. So x is the displacement of the body from the its mean position after time t in minute. See, these are the two forces here, kx and the m d square x dt means m x double dot. The restoring force means the shaft is when it is displaced from this position, mean position to displacement by x, when it is given the disturbance of force, and it will try to move to the mean position. Okay, this mean position. So this is the restoring force due to this stiffness of this rod or shaft. So that stiffness force will be there. That is restoring force. That is kx, and accelerating force is where moving. That displacement is in downward direction. So the velocity in downward direction x dot, and the x double dot will be downward direction. So accelerating force becomes negative because in downward direction, according to sign convention, downward direction negative and upward direction positive. So it is shown m x double dot. X double dot means d square x by dt square. So friend, here as per the Newton's second law of motion, accelerating force is equal to restoring force, and this written here accelerating force is equal to kx. So minus x double dot is equal to kx. Rewriting this equation, mx double dot kx, x double dot plus k by m, x is equal to 0. So comparing this above equation with the equation of motion of the simple harmonic motion. Okay, so what was the equation? X double dot plus omega n square x is equal to 0. So omega n is replaced by, or compare with this one, omega n square is equal to k by m, or omega n is equal to under root of k by m, and its unit is radian per second. And here but this omega n is equal to 2 pi into fn, or fn is equal to frequency of oscillation in omega n divided by 2 pi. So this is in hertz. Okay, this is in hertz frequency. So lastly, the answer is what? Our fn is equal to 1 by 2 pi under root of k by m in hertz. This is the final answer to find out this for this transverse vibration, friends. So you are learn very much, and you can, using this formula, you can find out the transverse vibration. Here k is important. So what is the k? Value of k? The stiffness of the how to calculate the stiffness? The weight upon del. So del is what? Deflection. Deflection is what? Deflection of that beam, or that is the deflection of that rod, shaft. That various conditions may be there. This mg by del. The account to deflection, the k, there is a relation between the k and deflection, inverse relation. Okay, this is very important, and we are going to study in two next slides the relation between the deflection and the stiffness. Substituting this equation, what will happen here? This frequency, see this 1 by 2 pi mg del by m, this 1 by 2 pi under root of g by del, and lastly, just solving this equation, the frequency of this is 0.4985 in the denominator under root of del. Del means frequency, that del means static deflection, and this frequency in hertz. So frequency again in depend on the deflection. So friend, here the relation between the static deflection and natural frequency of transverse vibration for the different types of beams we are going to study here now. The value of static deflection and the natural frequency of pre-transverse vibration depends on the types of beam and the load condition. So the various types of beams and load condition already we are studying in strength of material subject, but we are revising it, and I am giving you directly formulae, not derivation for this del, for the each condition and their relation. What is the Fn in that case? Directly I will give you the tabular form, the different beams with the different load condition. This table shows the static deflection and natural frequency relationship, and there is a different types of this. Various 8 cases are there for types of beam and load condition, respective load condition. The first condition is the cantilever beam is fixed at one end and free at one end, and length of L, and W is the weight at this end. So what is the deflection in this case? WL cube divided by DEI, E capital I. E is the elasticity of modulus of elasticity, and I is the moment of inertia for this weight. Okay, so WL cube, L is the distance, this distance, and W is the weight here. So through this formula we can find out the del, and when we put this value of del in this equation, we can find out the natural frequency. So this is the relation, this is the formula derived, and directly it is written here. And in second case, see, this is the UDL condition. In this case, this mass constraint of this shaft or this beam we have to consider, because it is UDL. Okay, in this case we have to consider that also. Weight of the mass we have to consider of the weight of this shaft. Okay, that we have to consider. The UDL is the distributed here, and its deflection WL is to 4, in denominator 8 EI. Okay, and this frequency becomes 0.621 del. So this is the MC is introduced here in this formula, or to derivation, we have to introduce the weight of this. In few cases, means where there is a UDL, I will add this MC. MC means mass of constraint. Mass of constraint means mass of the shaft or mass of this beam. We have to add it. So third case is there simply supported beam. Here we are not considering mass of constraint. This is the del, value of del, deflection. Okay, these are the formula derived. Already you have studied in strength of material, and this is a frequency formula. So we can calculate by using this one. The next condition is the fourth one, simply supported beam with an eccentric point of load. Here load is applied at the center. This is the total length. The center load is applied, and both the is supported. Okay, load is applied at the center. But if load is not applied at the center, at different than this distance is A and B, they are not equal. Here L by 2 are equal. In this case, this del becomes W into A square B square divided by 3EIL. And this case, when the load is applied at the center, WL cube divided by 48 EI. Okay. In this case, the frequency is 0.4985 del. And in this case, again, same frequency we have to calculate. But value of del is different. Calculate the value of del, it is the point load which is not at the center. Next case is the simply supported beam with the UDL. Here UDL is there. Similarly, the del, value of del, we can calculate by using this formula. And here MC is again introduced, W1 by G. W1 means the weight of this beam or load of this beam. Means that its self weight we have to consider in this case. When there is a UDL, there we have to introduce this MC here. This value of MC, this is we have to introduce in this formula. So both ends are fixed and load is eccentric load. That may be not in center. Both ends are fixed and load is moving, flexible. So in this case, again this formula and the previous in simply supported beam with the eccentric load and the same formula for the frequency. Seventh one is the both ends are fixed and at the center. In this case, this is the formula for the deflection, WL/4 192 EI, and here is the MC is added. Why this MC is added? Because this is suspended. This plate is suspended and load is applied at the center, not at the end. That's why I have to consider the here in this case. And again, a similar way, the both ends are fixed and UDL is there. That's why again here MC is added. So we can find out the del deflection by using this formula, W square as L/4 divided by 384 EI at the center. We have to consider. Okay. And similarly, this natural frequency you can find out by using this 0.571 under root of del. This is the formulas are given to you. So friend, note a shaft. If suppose in case of the shaft supported in short bearing, okay, the ball bearing or flexible bearings is assumed to be simply supported shafts. When the shaft supported long bearing means journal bearing, suppose it is considered assumed to have both ends fixed and the beam is not given, then assume simply supported beam. In case of the journal bearings with the shaft, we have to consider that beam is simply supported beam. In case of the journal bearing, okay, this is for your information, friends. So what you learn from this video, so that you have to, the outcome you have to write it, and you will learn by using your self-assessment only. So friends, thank you very much for watching my video, and if you are not subscribed my channel,